Good morning. In this video, I'm going to consider exercise 15b, which is to be found on page 26. So this is a typical exercise about calculating the size of an area. So it's a typical application of integral calculus. Well, what do we have? We are dealing with a rather simple function. We are dealing with the following polynomial: x to the power of 3 minus 3 times x squared plus 6. Here on the left you see a picture of the graph of that function. So what is our problem and how are we going to start? Well, let's read the exercise. Find the area enclosed, so the area enclosed by what? By the polynomial and the tangent through the local minimum of P. Okay, so since we already know how the graph of this function looks like, well, it's not difficult to paint a picture of the situation. So it's clear just from the picture that here we have the local minimum, so there's Tiefpunkt. If we draw the tangent, well, of course, since this is a local minimum, the tangent to that point is parallel to the x-axis, so slope 0. So here is the tangent, and then you see here the tangent together with the polynomial enclose an area here, and our task is precisely to find the size of that area here. Let's call that area A. Okay, so this is our problem. We need to find the size of that area. However, before we start with that, well, we're of course going to need two things. First of all, we need to know the coordinates of point T, and in addition, we are of course going to need the equation of the tangent. So let's start with the local minimum. So in order to get the local minimum, well, we take the derivative of P, which is 3 times x squared minus 6 times x. We set that derivative equal to 0. We solve for x like this. So we get x equals 0 or x equals 2. I mean, this should be right if we consider the picture. Here is 0 and here is 2. However, nonetheless, let us quickly check whether a x equals 2 is in fact a local minimum. So let's take the second derivative. P double prime of x is 6 times x minus 6. And let's plug 2 into that second derivative. And then we get here 6 times 2 minus 6, which is 6, which is bigger than 0. So we have in fact a local minimum at 2, or a Tiefpunkt with coordinates 2. And if you plug 2 into the function equation from the beginning, you see here the y coordinate is also 2. So we have a local minimum there. And just a remark, if you take x equals 0 and plug it into the second derivative, you get here minus 6. So this means that x equals 0, we have a Hochpunkt. However, we are not going to need that. So this is our Tiefpunkt. And as I said before, the next thing we are of course going to need is the equation of the tangent. And well, as I've explained before, since this tangent here is parallel to the x-axis, the slope of the tangent is of course 0. So the tangent equation just is y equals q. Okay, and now since here this point here has coordinates 2, 2, we know here this distance is also 2, so q equals 2, and our tangent equation is y equals 2. So this is my tangent equation and this is my T-point. So far, what we've done so far has nothing to do with integral calculus. This was just differential calculus. However, now in the next step we need to find area A. The problem is, how can we calculate the size of that area? The problem is we cannot simply apply an integral, because this area A is not just the area between a curve and the x-axis, and the integral is just good for calculating areas between curves and the x-axis. So we need to find a way to get A. Somehow, with the help of areas, we can calculate. So the idea here is rather obvious. We draw this additional line, and then you see here the whole area here, like this. The whole area here, well, that's the area between the x-axis and a curve. So we can calculate the whole area with the help of an integral. In addition, here we have just a rectangle, and we can calculate the size of that rectangle. So the area A is going to be given by the integral from a point we do not yet know up to 2 of p of x dx minus the area of the rectangle. Okay, so this is what we are going to do. So if you consider this here, the only thing that is missing is, well, we are going to need this point here, not only here in order to get this number here, but also in order to be able to calculate the size of the rectangle. So let's call that point Q. How are we going to calculate point Q? Well, that's not difficult. Point Q is the point of intersection of the tangent T and the polynomial P. So what are we doing? Well, we just calculate the point of intersection by setting the tangent equation equal to the equation of the polynomial, which leads to 2 equals x to the power of 3 minus 3 times x squared plus 6, taking everything on one side, and then just calculator solving for x like this. And then you see here x equals -1, so here we are at point -1, and Q has coordinates -1, 2. And now we are almost done, because now we can calculate the size of our rectangle. Here, side 3, this side 2, so the rectangle is 3 times 2, which is 6. And the only thing missing now is the integral from -1 to 2 of the polynomial. Okay, so let us write down the antiderivative. Here the antiderivative is given by 1 over 4 times x to the power of 4 minus x to the power of 3 plus 6 times x, and the whole thing at 2 and -1. Doing the calculation, I mean, as I said, you can just plug this here into your calculator, and doing the calculation leads to 12.75. So in the last step, we calculate the size of our area by taking this area minus the rectangle from above, so it's 12.75 minus 6, which is 6.75, and that's it. That's the whole point of this exercise.